Hello everyone, welcome back. So today we want to talk about the derivatives of the inverse trig functions. So our goal is then kind of understand and recall the basic details of inverse trig functions and also be able to find their derivatives and do some example or two. So first off, remember with inverse trig functions, what they are is, remember also in general what an inverse function is a way of, or inverse functions are ways of kind of undoing other functions. Okay, so a good example, of course, are exponential functions and logarithmic functions. But sometimes we have to do use inverse trig functions. Oops, spell that verse to undo trig functions to find angles. Okay, so let's imagine. Let's do a quick thought idea. So let's imagine this is the unit circle. So the unit circle is a circle where the radius is 1. And let's say we have an angle somewhere. I was drawing the first quadrant, but it could be anywhere. And of course, remember this distance, of course, is y, and this is x. And here's your angle. Let's call it theta. Theta is often used. Of course, you can call it anything you want. Then, for example, if we say that the sine of theta is equal to y, okay, then if we take the inverse trig function of both sides, we can also say that theta is equal to the inverse sine of y, okay? So also one thing to keep in mind, anytime you see an inverse trig function, an inverse trig function of a number is actually an angle, okay? And so these things undo each other. So if we need to find an angle, that's where we do it. Essentially, think this is taking, it's not technically true, but think this is taking the inverse sine of both sides and cancels it out. You've probably seen this before in your trigonometry class. Okay, so that's what an inverse trig function is. It basically is just an angle. All right, now there are also restrictions on these things. Let's actually take a look at Desmos and graph a couple of these. They can remind you what they look like. So go to Desmos, go to the graphing calculator. So first, let's just graph sine. So y equals the sine of x. Let's zoom in a bit. Okay, of course, you know what sine looks like. Now, remember also, if you think about the line y equals x, graphically to find the inverse of any function, you flip the original function, the red function, over this blue line, line y equals x, to get the inverse. And of course, since sine is not 1-to-1, we have to take a part that is 1-to-1, basically going from negative pi over 2 to pi over 2. If we do that, then we can write this. A couple ways we can write it, okay? Let's write this as y equals, you can find the inverse trig functions on Desmos. So click on the keyboard down here, go to functions, and actually when the first ones comes up, let's do inverse sine of x, x, okay? And what you see, as I mentioned, let's get rid of this. It takes the part that goes here from basically negative pi over 2 to positive pi over 2 and flips that over the line y equals x to get this green line. So the domain of this function is -1. The inverse function is -1-to-1. That's important. Okay. So for example, you can't take the inverse sine of something outside of 1. Another way we can also do inverse sine is something called arc sine. You may have also seen that done as well. So if we do ARCSIN, that's the same thing. Arc sine of, say, -2 or +2 is not defined. Your range or domain is only between 1 and -1, but does include -1 and +1. Okay. Now, so what we're going to do then is, of course, then find of this inverse function. So let's actually turn off the original sine graph for now, and also this. What we want then is the inverse function of this. Okay. Now, we're not going to go through the details of actually how it's derived. You can find that in textbooks or other videos about this. Let's just take a look over here on the left-hand side and see what that looks like. Okay. So you're also going to see a symmetry, and I've also grouped these kind of with sine and cosine first, and also for their domains. So these are also domains of inverse sine and inverse cosine from -1 to 1. Okay. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. And you can also partly see the reason for the domain restriction. If x was bigger than 1, this would be a negative under the square root, and of course it'd be imaginary. We can't do that for real numbers. Okay, So that's the derivative. Let's graph that and see what that looks like. See if that appears to be a logical derivative of the inverse sine. Let's just get rid of this for now. So let's graph y equals 1 divided by 1 minus x squared. Okay, now here, ignore these parts out here, but here we're just looking between 1 and 1. So once again, our function, original function, remember we're talking about the slope of the tangent line. So if you notice, this function is always increasing, so our slope is always going to be positive, and it's increasing the most here and at -1 and also at +1. Okay, and the shallowest is right here, and that's what we see. Okay, we see basically our slope going to infinity. So for our tangent line going to infinity here and here at 1 and -1 and 1, that's what we see here in our graph. And also right here, the shallowest part, the lowest part, the minimum, or the shallowest slope is still positive, is right here at 1. That's reasonable. Okay, and that's the derivative. Now, the derivatives of the others work similar ways. Let's actually turn these off. Let's actually just quickly graph cosine, and we'll see a similar thing. So let's do, this time we do it y is, repeat what I did before. So let's do the graph of the inverse cosine. We'll go to functions and inverse cosine of x. Oops, it should be an x. Okay, there we go. Now, you notice back here, we have essentially the same expression, except just has a negative in front of it. Okay, there's a symmetry in all these. That's true of all these. The rest of them we'll see in a moment. But let's do that. So I can do is actually just copy this and paste it. And I'll just put a negative in front and see if this makes sense. Okay, so for our original graph, let's zoom out just a bit. Okay, it also goes from -1 to +1, the range, the domain rather. And so this case, similarly, is kind of the inverse of the reverse of what we saw with the inverse sine. Is this one is always decreasing, and it's basically the slope of the tangent line is going toward -infinity here at -1 and also here at +1. And the shallowest decrease right here is in the center, and that's what we see right here. Once again, ignore these other parts, but just look at the part between 1, -1, and 1. So that's reasonable. Right. So those are the derivatives. Notice all these have certain symmetry to them. For example, a tangent, derivative of tangent, inverse tangent is 1 over 1 plus x squared. And also both these, you can plug in any x you want, all real numbers. And this one for tangent is the positive version. Cotangent is the negative version of the same function. And then for cosecant and secant, your range there, or domain rather, has to be basically where x is greater than 1. They're positive or negative. The absolute value has to be greater than 1. And here, this expression, you see once again, negative or cosecant has the negative version, and secant has the positive version. All right, let's take a look at just a couple quick examples. And so we're not going to go through the details of where these functions, how they're derived. You can see that in textbooks or other videos on the topic. Let's just say, let's find the derivative. Okay, so number 1. So of course, these derivatives work in all other kinds of functions. So let's say we had, let's say f of x was going to be x squared times the inverse cosine of x. Okay, so this is a product, so we of course use the product rule. All right, so f prime is going to be, doesn't matter which one we start with. I'll start with this one. So take the derivative of the first function. Derivative of x squared is 2x times the second function, which is the inverse cosine of x, and then plus the first function by itself, then times the derivative of the inverse cosine. And once again, that here, according to this, is going to be -1 over the square root of 1 minus x squared. And of course, here we also have that same domain restriction working with x. X has got to be, we can only consider x is between -1 and 1, even for x squared. All right. And then we can also just clean this up a bit. And so this is just going to be 2x times the inverse cosine of x plus, or sorry, it should be minus rather. That's where the minus here. Minus x squared over the square root of 1 minus x squared. Okay. Now, let's do one more that involves the chain rule, and let's also do it a bit differently. All right, so let's say we have this. Let's say we want to do the, let's say y is equal to the inverse tangent of, let's say, e to the 2x plus 1. So something a little more interesting. Okay. Now, this is obviously going to involve the chain rule. So this is, now the next part is not something you have to do, but it's also good practice with using something called U substitution. Okay. So what we're going to do then is we're going to say we're going to let, once again, this is optional, but it can make things a little bit easier to work with. Let u equal e to 2x plus 1. And so if I substitute that in, what's called U substitution, I say substitute it in, what I'm going to get then is going to be that y is equal to the inverse tangent of u. Okay, now why is that useful? And maybe a lot of times to make it look a little bit easier to work with. All right. Now let's also do one more thing. U is a function of x. So if I do, let's actually do this first. And let's take the derivative. All right. So the derivative of both sides okay, of course, the derivative of just y by itself is just dy over dx. The derivative of this, using our rule, okay, of tangent is going to be 1 over x, or actually 1 over u squared in this case. 1 plus u squared, okay. I should make that look a little bit better. 1 over 1 plus u squared, just using u right here. But here, think about the chain rule, that u is a function of x, so then it's going to be times du over dx. Okay, so I actually need to find that. Okay, I'll just say and du over dx. Let's look back at this, du over dx. Okay, so u is e to the 2x plus 1. So the derivative of this, of course, derivative of the constant is 0. So the derivative of e to the 2x is going to be, once again, the exponential is just e to the 2x. Okay, then once again, the chain rule, the derivative of 2x is 2. And that's going to be 2e to the 2x. So now let's substitute everything back in. So with the substitution, you substitute back in with the original variable. So substitute, I'll say substitute back. And so what we have then is dy respect to dx is going to be 1 over 1 plus u squared. Remember, u was e to the 2x plus 1 squared. Then the derivative of the du dx is this, 2 times e to the 2x. And then we can also just put those together. And we have 2e to the 2x over the same denominator, 1 plus, in parentheses, e to the 2x plus 1 quantity squared. Now, once again, the u substitution is not necessary, but often can be helpful just to kind of make a complicated function a little easier to work with, a little easier to understand. Okay, so let's kind of review what we did. So today, this has been a short video, but basically all the rules of differentiation from here, all you showing this video is just basically what the rules are for these inverse trig functions, and reminding you a few things about their domains and how they work. So we learned basic kind of read some of the basic domains. So remember our domain in these functions. So fortunately for inverse tangent, we can actually plug in any e we want. Okay, and also it's true for the exponential. So here we have no limits on what x can be, but other functions that we see, that's not true. So you have to be careful of that. And we just found the derivatives. Of course, you can use those same derivatives in any kind of function involving product rule, quotient rule, chain rule, higher derivatives, and so forth. Okay. Thank you. Have a good day.